Kuala Lumpur continues to transform with world-class infrastructure among them. Merdeka 118 stands tall, a global icon of development. Supporting this mega project, beneath the surface lies a key component, the Belfield Tunnel 118, designed to improve traffic flow and access around the tower. The Belfield Tunnel is a reinforced concrete, underground vehicular tunnel located beneath Jalan Maharajalela in Kuala Lumpur. Measuring approximately 1.5 kilometers in length, the tunnel was designed as a double-deck vehicular tunnel, provided direct access to Merdeka 118 tower and basement parking.
Okey, sekarang kita berada di penghujung tunnel di mana entrance untuk masuk ke Menara Wawan itu.
It is constructed by Gamuda Berhad, one of Malaysia's leading infrastructure companies, and developed by PNB Merdeka Ventures SDN-BHD, a subsidiary of Permodalan Nasional Berhad, PNB. Behind every successful tunnel lies a well-executed plan. Let's explore the key methods that made the construction of Belfield Tunnel possible. Before construction began, the team carried out soil studies and site investigations. Boreholes were drilled to interpret the subsurface profile based on location shown in diagram. This helped team plan safe excavation and control groundwater effectively. The Belfield Tunnel includes 9 tunnel types, A to L, and each with different lengths and installation methods based on site needs. The Belfield Tunnel uses the top-down method for tunnels A, B, C, H, ME2, ME3, and ME4, while tunnels J, K, and L are structured by using the bottom-up method. This method begins with installation of diaphragm wall, followed by casting the roof slab. Once concrete reaches 75% strength, temporary openings were created at every 30-meter interval along the tunnel. Excavators were lowered through these openings to begin staged excavation, digging in layers of up to 3 meters. The soil was transferred to a staging area and lifted to ground level using clamshell excavators. Excavation continues until the intermediate struts, deck slabs, and finally base slab were cast. The excavated soil is loaded directly by excavators into standby dump trucks at ground level. Only approved trucks are allowed to transport the material to designated dumping sites. For tunnels J, K, and L, excavation was done using the top-down method, soil removed from above in stages, but the structure was built bottom-up, starting from the base using box culverts. To support underground construction activities, proper lighting, dewatering, and ventilation systems were installed throughout the tunnel. Non-working areas have at least 50 lux, while active excavation zones are required to meet a minimum of 100 lux to ensure a safe working environment. Next, a dewatering system with sump pits and pumps is used to control groundwater during excavation. Water is pumped out at every level and discharged safely to keep the water table at least 1 meter below the excavation base. Next, a ventilation system is used to supply fresh air and remove dust or fumes during excavation. It includes 1 blower fan and 1 exhaust fan, running continuously when work is ongoing. In summary, careful planning and a combination of construction methods ensured the Belfield Tunnel was built safely and efficiently. Building a tunnel beneath a bustling city is no easy task. From the earliest investigation to the final stages, numerous obstacles had to be overcome. Now we focus on the complex excavation process. Excavation in Belfield Tunnel is a highly coordinated operation. Cranes, excavators, and dump trucks work seamlessly beneath the tunnel's top slab. For the top-down excavation, excavators, EX120 and EX200, are lowered into the tunnels through temporary openings using a crawler crane. Inside the dig soil in layers, each up to 3 meters deep, the soil is moved to a nearby staging area where a telescopic arm lifts it to the ground level. Dump trucks then remove the soil via designated routes. This process repeats every 30 minutes, creating a continuous excavation underground. This careful and repeated excavation method ensures safe and efficient progress throughout the entire tunnel process. Another major challenge during construction was managing the naturally high groundwater level at site. The site has high groundwater that can seep into the excavation. To control this, dewatering is done continuously during excavation. Sump pits will collect water at each excavation level. Keeping groundwater at least 1 meter below the excavation base prevents soil problems and collapses. Building a tunnel in the heart of the city means working around busy roads and public spaces that require careful traffic and safety management. Excavated soil is transported using designated routes along Jalan Syed Putra and Jalan Maharajalela to ensure smooth haulage. Strict traffic control measures are in place to protect public safety and maintain flow during operations. Since the tunnel is close to the monorail alignment, any work within 6 meters required a special permit. This will ensure all safety and regulatory requirements are fully met. 2021, the Belfield Tunnel was under construction amid Malaysia's COVID-19 lockdowns, which greatly impacted its progress. During strict movement controls phase, all non-critical works including excavation and structural activities were suspended and causing delays and requiring project rescheduling. When work resumed, strict SOPs were enforced. Tunnel works and earth haulage had to continue with limited manpower, while key tasks were reprioritized. This process and procedure being slowed down and adding to the project's challenges during pandemic. In addition to overcome physical and operational challenges, the Belfield Tunnel project also focused on sustainable practices. Through the use of advanced technology, the Belfield Tunnel used the top-down construction method. Where permanent structures were built from the top level downward, this method helped reduce noise, vibration, and dust at the surface, and making it environmentally friendly. It also allowed early construction of permanent slab and basement wall, which improved overall structural stability and safety during excavation. Next, let's look at how automation plays a role in ensuring tunnel efficient and sustainable. The Belfield Tunnel is equipped with a building automation system, BAS, which is an integrated platform that controls and monitors essential systems such as lighting, mechanical ventilation, fire detection, and overall management and maintenance. This system automatically adjusts lighting levels based on usage or time of day, ensuring energy is not wasted. Ventilation systems are also regulated to maintain safe air quality. Inside the tunnel, especially when vehicles' emissions accumulate, fire alarms, emergency fan and smoke control systems are all connected to BAS, allowing immediate response in case of any incident, and all from a centralized control room. By automating these systems, BAS not only increases operational efficiency, but also significantly reduces the tunnel's carbon footprint. Next, the tunnel is also supported by Smart Traffic Integration System, was designed to monitor and manage traffic conditions in real time. From the control room, operators have full access to live CCTV feeds, traffic sensors, and digital signage that help regulate the flow of vehicles inside the tunnel. This integration ensures a safe, responsive, and energy-efficient driving environment, while reducing manual intervention and enhancing tunnel operations overall. The Belfield Tunnel is a result of strong teamwork, smart planning, and innovation. Despite challenges, it now stands as a proud part of Malaysia's modern infrastructure.